Good morning, everyone, and thank you for joining today's webinar from Spec Innovations. Today's webinar is titled The Future of Systems Engineering. My name is Joanna Moore, and I'll be your moderator today. First, let's go over some quick housekeeping. During the presentation, feel free to send us questions, and we will get them answered in the question and answer part of the webinar. The webinar is being recorded, and we will make it available to you after the live presentation, so be sure to keep an eye out for it in your inbox. Now, I would like to introduce you to our presenter, Dr. Steve Dam. He'll be sharing with where systems engineering came from and where it is going. Dr. Dam is the president and founder of Spec Innovations, as well as one of our DODAF training instructors. He has been involved with research, experiments, operations analysis, software development, systems engineering, and training for more than 40 years. Dr. Dam is a member of the LML Steering Committee. He has also received an Expert Systems Engineering Professional certification from INCOSE. Currently, he is applying systems engineering techniques to various DoD, DOE, and commercial projects. Feel free to send Dr. Dam any questions through the LinkedIn user group or send him an email. And now I'll hand over the controls to Dr. Dam, and we'll get started.
Thanks, Joanna. So today, a lot of you, several of you may have already seen a presentation from me on this topic at NDIA Systems Engineering Conference back in October. And then again, more recently, in February, we were at the Aerospace Corporation's Systems Engineering Forum. And that kind of is an interesting, was an interesting place for it, because actually that's how this all got started. So first of all, why the question? It turned out that I was at another systems engineering forum by the Aerospace Corporation back spring last year, in 2018, and someone in the audience stood up and said, SysML is the current systems engineering approach, but 10 years from now, it's likely to be something else. And that kind of got me thinking about, well, what is the future of systems engineering? And that then begs other questions, which is, well, what do we need that we're missing? Why isn't SysML enough? How will the technology improvements enable better systems engineering? Why do we have to wait 10 years for everything? And then how can we predict the future? Of course, it's easy to predict the future when you've lived it so many times in the past. So let's talk a little bit about that history just briefly. So a lot of people think that systems engineering started back with the pyramids and back in the ancient days when some of the amazing feats of engineering that were created, and no, I don't think they were by space aliens. But this, by the way, this slide set on the history is coming from a colleague of mine at George Mason University, Peggy Browse's course, which I was fortunate enough to be able to teach for her several times. Anyway, so if you think about that long ago, that could be, but they didn't necessarily document their processes like we do today. So a little different if we fast forward to the machine age. That industrial revolution and assembly lines and things like that clearly required systems thinking. There was a lot of process discussion back then, particularly how to improve processes and create higher quality processes. And so that was used pretty extensively. So I think, a lot of people feel that's a really good start for it. But certainly by the space age, we had really what we think of today as systems engineering. And a couple of the progenitors of this was Ramo and Woolridge, and they were some of the early developers of the systems engineering as we know today. That became Thomson, Ramo, and Woolridge, TRW, which of course has more recently been procured some years ago now by Northrop Corporation, so Northrop Grumman. So there's a long history of this, and this work has gone on for quite some time. I know some of the things that we particularly start from was work done by TRW in the 60s. Some of the analyses we looked at and tools have actually evolved during that time period. So today's advancements really give us some feeling for the speed, how fast the technology is changing. I'm sure all of you feel like whipsawed that you're always you're amazed that, you know, it seems like just a few years ago we were using normal rotary dial telephones, and fast forward not that many decades, and here we are using these smartphones which have computers in them that are amazing and can do amazing things. By the way, this slide comes from the Systems Engineering, Incosi's Systems Engineering Vision 2025. So another presentation I saw recently was from a Dr. Kirk Bourne, and he talked about this complexity part of it. Well, that's going out of sight too. So not only do we have the speed of change happening fast, but we also have this complexity going on. And so when you look at, and he used an example of how much data you collect in a year for a US commercial airliner, just the jet engines, I think was really what he was talking about, the sensor data on the jet engines. And he said it's on the order of a zettabyte. And I had to look that up, and that's a lot. That's 10 to the 21st bytes of information. I still remember when we worried about each byte of information. So it's really, I mean, it's phenomenal what we have to do with and deal with data. So some of the major technological advances we're seeing today, particularly the automated vehicles. I've been dying for this for 20 years. I'm excited about this event. 3D printing. This is going to do for us what the software people have always had, is some way to quickly, rapidly prototype things and objects and do the physical thing. Of course, this gets close to that old Star Trek Enterprise next generation replicator idea. We're not there yet. And of course, drone delivery, that's happening. I actually didn't see a flying one the other day, but I was on the campus at George Mason University, and there was actually a little robot ground vehicle delivering things. I believe it was food on campus. So this is real, and this is happening today. And of course, we've got artificial intelligence, Internet of Things, on and on and on. There's lots of technological advances that we see coming. So with that complexity and technology increasing so rapidly, how does systems engineering need to evolve to deal with that? How can we support this? Because you still need system engineering. You can't just make stuff and think that it's going to work well as a system together. So one of the things that's happened is Incosi has an initiative for the future of systems engineering. It's headed by a friend of mine, Bill Miller, a great guy, and he's looking for volunteers, by the way. So always, if this is something you're really interested in, what they're trying to do with this initiative, I'm going to give you a few points from his slides on the subject here. But it really is a good way to help develop this vision. So the Incosi Fuse initiative, the purpose that's in the charter is that, you know, position systems engineering to leverage the new technologies and collaborations with the allied fields, enhance the systems engineer's ability to solve the emerging challenges, promote systems engineering as essential for achieving success and delivering value. And these are some of the things that trying to get to with what does it look like and what's stopping us from doing it. And by the way, this initiative initially started, I believe, in the previous 2018 IW. Maybe that's what generated that gentleman's question back at the SE Forum in 2018. Unfortunately, that was the year I missed, so I didn't even know this was going on. We had no idea this was happening until actually this IW was our first. Wow, okay, that's very cool. So as we go through and look at the specific things, one thing really struck me, which was systems engineering is too slow to keep up with AI advancements. I'm going to talk about that a little bit more later. Why is that? Also, the president of Incosi, Gary Rodler, again, another great guy who's running the organization today, he had this vision of the future of systems engineering and what it looks like in the environment. So particularly these keys of, it's going to be dynamic and non-deterministic evolutionary. Cybersecurity and assurance are needed to be integral, not bolted on. I can't say how many years I've been saying that. And new approaches to verification and validation. We're going to need some new things, particularly how do we deal with this evolving, adaptive learning systems? Well, in a sense, maybe we know how to do that because we do that with people, and they're pretty, their behavior is challenging as it is, and we model that and we deal with that in the V&V world today. But still, we got to think about a little bit more the automated side of that. Ongoing modeling and simulation challenges. Again, some specific things about how to deal with that and look at that as part of the process. Ongoing operational changes, of course, that's going to be a key part of it, and particularly our interaction or the people as people with these AIs, and how do we deal with that? And then changes required for a literate workforce. How do we train people to do this better? And again, heavy focus on systems engineering. What are our roles? What do we need to do? How do we need to adapt and learn better? So again, that's a great initiative. Highly recommend getting involved if you're interested. But let's address a couple of these points, or try to address most of these points. So why is SE so slow today? So one of the things is we can look at how our languages have evolved. In the 60s, we used flowcharting. I still remember, I may even still have my old template that I used to the little drawing symbols, and it was great, and it was very useful for that purpose. Then we got into something in the 70s, and particularly I used it heavily in the 80s, something called data flow diagramming. And that was a good way to look at data. And we separated, for software particularly, was separating data from control. And that was a key thought behind software. And we now have that with the software levels that modularization that goes on with modern software like Java. So in the 80s, they brought in a system called IDEF. If you're familiar with that, integrated definition, I think is what that stands for. IDEF 0 is almost the only thing anybody knows about, but in fact, there were 15 different diagram types in that particular group. There's also state machine modeling. Computer-aided systems engineering tools started getting popular. One of the first ones I saw that was actually that, as opposed to a software engineering tool, which both had the funny acronym of CASE. But the systems engineering, I'd say the one that was really truly a systems engineering tool was a tool called RDD 100. That traces its heritage back to TRW in the 60s. So that's that lineage I was mentioning earlier for that history. So that was a key one. One that spun off of that not long after that in the 90s was one called Core, and a lot of you are familiar with Core and its latest incarnation in Genesis. So that whole process, again, that's a lineage you can kind of trace back to, at least the theoretical lineage of it. It's not obviously the practical corporate lineage at all. Anyway, so in the 90s, we had, again, the enhanced functional block diagrams out of Core. And there was another thing that was starting up, which was the object-oriented analysis and design approach. Multiple different techniques were being suggested for that in terms of particularly different notations. They got brought together in something called Unified Modeling Language, if you're not familiar with it. And again, all software. You look at all of this, it's all software to this point in time. So in the 2000s, a group got together and decided that really we need a systems version of UML to help the systems engineers particularly be able to communicate better with the people using UML. So that was a key aspect of it. So that was something that was there. And here we are in the 2010s, almost to 2020, not far away now. And so, it's still SysML at the moment. It's the main systems engineering language people are using. But there is something called lifecycle modeling language, LML, that's been emerged and was derived from systems engineering techniques. In LML 1.1, the ontology included SysML in that particular standard. So it provides an ontology for SysML and provides a mechanism for using a data approach to creating diagrams, which is actually very useful for a whole variety of reasons. But it seems like we're kind of always like 10 years behind the software world. Why is that? I don't know, but we're gonna talk about that a bit more. So let me say, well, so go back to, okay, so we say all this stuff and say, well, what's really missing? What is it we need to do? Okay, so if we go back to fundamentals, we have to say, okay, we need methods to capture and visualize tremendous amounts of information. That zettabytes of data, what are we going to do with that? And how do we store it and retrieve that information? That's another key thing to think about. In other words, we need to not only have all the technical readouts, but all the programmatic information has to be captured too. It's not just simply about the data sets that we think about in terms of like performance, but cost, schedule, risk, decisions that were made, why they were made. Being able to capture that programmatic information is just as important and a key aspect of what we do as systems engineers. The difference between a system engineer and a program manager is a system engineer looks at cost, schedule, performance, and mitigates risk in all those areas for the system. The program manager does it for the program. So actually, fundamentally, they're very, very similar. And let me plug another thing by Innoslate, another product by Innoslate and PMI, which is integrating program management and systems engineering, methods, tools, and organizational systems for improving performance. This is published by Wiley, and it's a joint book that was put together by Innoslate and PMI, and a lot of hard work went into this particular book. So do recognize the synergy of the two disciplines. Anyway, that's a little bit of an aside, but so another thing we need is capability to move data around easily between applications, and that's a tough one. That I've watched for at least 20, maybe 30 years now, people trying to do this, move the data around between things, and just wasn't very easy or good. And it's like we could never come up with a really, really good standard that everybody could adhere to and adopt. And I know there's been some even more recent attempts, and maybe we're getting close to something, but it's really tough. And so fundamentally, we also need a language that enables decomposition and abstraction, right? I mean, that's pretty basic. And, we need a systems engineering language, not a software engineering language. Systems engineering and software engineering may both have S and E starting with them, but they really are very different in how you have to approach things and how you have to approach problems. Because in the software world, they can quickly make changes to things, they can test a little, build a little, test a little, that whole kind of approach to things. You can do that a little bit in the hardware world, but you have to be careful in the hardware world. It's really still a measure twice, cut once kind of environment. And then when you add the people, or the wetware as I like to call it, to it as well, that's a key part, right? Because we're part of the system. We're a key part of the system, right? All that stuff is for us to use as users. So ultimately, people are a key part of what we do too. So again, the language we need is something that needs to be simple enough that systems engineer can easily use it and anyone else can easily understand it. Now, I know you're saying, well, SysML does all this, right? Oh, of course. Well, why isn't SysML enough then? Well, let's look at it a little harder. So SysML, again, was developed to help extend. It was an extension. It's actually called a profile, which in normal English, that's just an extension. It gives you it basically was that extension on UML that was created. And so when you look at UML as interest level, Google Trends gives you all kinds of great information. I saw that used very extensively in Innoslate. And this is one that I've had now for a few years, and it always amazed me. So I looked at it, and as unfortunately they didn't collect the data before 2004. So I don't know exactly when it peaked, but it certainly had peaked at least by 2004 in terms of interest, right? And the reason for that is in this interim time, software developers have moved on, particularly to agile frameworks. Okay, so agile frameworks require functional requirements. That's what they want. They don't want the diagrams from UML, and it's really kind of one of those things that's kind of, I know, frustrating to people that that's the case, but that's what it is. So looking at that, say, okay, so that's, well, okay, still we could use it, why not? But the problem is that UML and SysML require experts to create and interpret these diagrams. That's really kind of tough because our job as systems engineers is we have to talk to everybody, not just the software people. We have to be able to talk to contracts. We have to talk to you know, the stakeholders, the generals, everybody in the system, all the way up and down. And of course, we have to talk to all the design engineers who have their own languages. You know, the mechanical guys and the electrical guys, they all have their own kind of languages. And our principal job, in fact, is to be a communicator. We are there to help people understand what's going on. So if you have to be an expert in SysML's lexicon and diagram specifications, who are we communicating with? Okay, that's not all the problem. So it's a little worse than just being not easy to understand. SysML is lacking many of the programmatic pieces of information: risk, issues, decisions, schedule, cost, as explicit diagrams or entities, right? You have to add that information in. You can, I mean, yes, you can create your own ontology within SysML, but yes, you're creating a language on the fly by doing that. So the lack of ontology and the need for more diagrams has been noted. There's a process going on. There's an RFP out, in fact, by OMG to help resolve this, but they're estimating this is going to be another 3 years at least before that's going to happen. So, well, what if there was already a language that was available to do this, provide that ontology and help fill in the missing pieces? And the answer is there really is. The lifecycle modeling language does that. As I mentioned earlier, 1.1 was extended to make sure it covered SysML. And you can go see it at www.lifecyclemodeling.org. Go download the specification. It's an open standard and completely available to anybody. Let me talk briefly about that for those who aren't familiar. So what LML has is a very simple taxonomy. There's 12 primary classes with 8 subclasses to those ones as the base set. SysML added a couple other a subclass and an individual class, the port, and that's a subclass of asset, and then the equation, which is used particularly for the parametric diagram, was added as a separate class. But the rest of the information was identical to what the baseline LML is. So having that set of bins, it's well defined, it's easy to understand, and they have many types to them, and the types are, many of them are identified within the specification, but you can have your own type of an action. So if you want to call an action a function, have a nice day, do it. If you want to call it an activity, yep, that's fine too. They're all actions. They're all fundamentally that kind of activity, a functional element. So again, as you walk through these, you see that commonality of things, and then using the typing to help get synonyms of things so they're together. That simplifies tremendously the bins of information. Where do I put things? I still remember when I teach DODAF to people, operational activities and system functions, people say, well, when do I use which? And that was always tough because some of that's from the perspective of the person who's doing the work and where you are in the development process. So, those are kind of the hard things. But if I consider both actions and you decide when they go, it's a lot easier. So that's an example. So that's, you'd say, well, gosh, that's awfully simplistic then. How could it possibly support all the different information I've got to capture? Well, there are relationships associated with each of these So there are relationships between each one of them. And again, that looks pretty complex when you start looking at all those relationships. But the nice thing is, we were very careful in the steering committee to create relationships that were in both directions using the same verb. That's a key part of this. So now I know if I have it's specified by, then the inverse of that is specifies. And so, and we use those things consistently through here. So again, it's a little simpler because in fact, the number you're dealing with is a lot easier to use. We also did things like making sure there was a common parent-child relationship, which is decomposed by and decomposes. That's really critical. And the same thing with the peer-to-peer relationship relates to. So again, you can add other specific ones as you need them, particularly for the asset we added orbited by, so we could do orbital locations associated with the physical assets as well. So that's a key part of it. Now, another aspect of it that adds to the ability to gather the full breadth of what you need is there are attributes on both. There are attributes on the classes entities, and then there are the attributes on relationships. And if you think about that, then I've got a language because my classes show me my nouns, my relationships give me my verbs, and so an attribute on the class is an adjective, and then the attribute on relationships is an adverb. So I've got the basis of a real language this way, and it is complex underlying it, but it's simple enough to get into and understand and get started with, and that's the key. Also, the language specified 3 specific mandatory diagrams for your system engineering, but you could do others as needed. So there's the action diagram, which is the functional behavioral diagram that we have. We also then do the physical diagram, which is the asset diagram showing the assets and the conduits, which is the pipes that transmit information between the assets. And then the third one is the spider, which is showing our traceability. So what this is doing is showing the different objects that we have, object types and classes, and their relationships between them. So again, a nice way to visualize and see that information. But if you have other classes of information like time, so you want to do timelines, right? I want to do risk. Oh, a risk matrix or risk burn down chart. Those are things that are really helpful for those kind of things. So those are common visualizations of these things. And in the standard, they recommend specific ideas for that, but that's broader than that set. So the future systems engineering really kind of is here. So let's talk about that. So let's go back to Gary Rodler's specific items. So dynamic, non-deterministic, and evolutionary. Okay, well, lifecycle modeling language takes a relationship approach. You know, with over 50 relationships, the systems engineer is able to manage the system by understanding their parts and their relationships. Okay, so you have that. And then the Innoslate tool, which is the only tool so far to incorporate LML explicitly, has both discrete event and Monte Carlo simulators. Okay, so again, those help you deal with the fact that you can have randomness in decisions, in the numbers and information, and you can start dealing with this non-deterministic, and of course, being able to do simulation with it directly gives you that ability to do the dynamics. Another aspect was Gary mentioned was the cybersecurity and assurance need to be integral, not bolted on. Could not agree more. So one of the things about the action diagram you may or may not have noticed, but instead of using constructs for the logic, it uses a special case of the action. Now that sounds kind of trivial, and maybe it seems like that's overly simplistic. But if you think about it, what that is those are your decision points throughout your process. Now those decision points can occur at any level of decomposition. Now that's critical because if you're doing, one of the key tenets of security is defense in depth. And the idea is that each layer can deal with things. Okay, well, those decision points that we now have as a type of action now are allocatable to what does them. So if that's your cybersecurity, if that's your information assurance guys, if that's command and control, you can identify who or what is doing that action. And that's critical to have that in. Yes, you can do that with other languages, but you have to remember to do it. And you have to force yourself to have discipline that most people don't have, including myself. I've been known to do the same thing with the other languages. This forces that to happen. The other is Innoslate itself is one of the most cyber secure tools out there for the U.S. defense. It's completely made 100% in the United States, and it's available on classified networks and private servers. So again, I think we've handled some of those kinds of issues with that security side of things. The next one was new approaches in V&V. Well, Innoslate provides a direct V&V support for the lifecycle. Systems engineers can easily see the behavioral changes as the data and the models are changed. There's a test center in Innoslate as well, and documents view provide the means to conduct the test planning early and capture the results during and after V&V. So this gives you that documentation of it and lets you do something that I keep telling people as they're coming down the V, they're responsible for what's going on the other side, and they need to make sure that the other side coming up the V and the V&V side of things is getting what they need, including a good test and evaluation master plan, including your integration plans, including things like transition plans, plans for operations and support, training. All those things are really the job very early on in the life cycle to at least start that process. It won't be done until you get to that point, but at least if you started, you kind of know how it is, the system's going to get bought off, how it's going to be transitioned, and how it's going to be used. And that's critical to document that early in the process. Ongoing modeling and simulation challenges, okay? Well, sure enough, having simulators built in to do this decision process make a big difference. And it will help you deal with your artificial intelligence. You can actually program what the kinds of decisions you might expect. Again, and then you can decide, you can allocate those decision points to who or what does it. It could be a person, it could be the artificial intelligence. And that's a very simple way to start that process and understanding when do you want to use AI, how do you want to use AI, how does it fit into the overall side of things, and then be able to model it and see what the behavioral aspects might be, particularly as you put the randomness in. That's a very powerful way to do it. The next one was ongoing operational changes. So of course, the key is, of course, taking a digital engineering approach to concepts of operations. We have a ConOps document. We have a whole methodology for doing that development. And of course, within the tool, it's built in. If you look at our ConOps, we actually implement the whole idea of how to create a good set of scenarios to even do as part of your ConOps. So anyway, that's all part of it, what we're doing. And of course, we're always looking to integrate the operators into it so you can actually create an operational view from externally of the database. And so we have actually done that several times. We call that architectured operations. And you can actually do that whole life cycle within the tool. And of course, changes require a literate workforce. One of the things we found out there is people gravitate quickly to the lifecycle modeling language. They understand it, it's easy to work with. We recently had, I had a friend of mine tell me a story where they were in a meeting and he was showing some SysML diagrams, and then he was showing some LML diagrams, particularly the action diagram. And there was a contracts person in the room, and she basically said, wow, I didn't get that other stuff, but I get this one, which is pointing to the LML diagram, the action diagram. So again, it's communicating to a much broader set of people, and that helps tremendously in our primary job, which is making sure people know what they're doing, how they're doing it, and it's relatively simple and easy to work with. Technology improvements. So how will technology make better systems engineering? That was another question we had earlier. So some of the emerging technologies of the future kind of are already here. Cloud computing, yep, already here, been here for decades. We started development of Innoslate on the cloud, did our first release in 2012. So yes, we've been cloud native since 2012. The artificial intelligence, well, we've been using natural language processing and pre-trained machine learning algorithms for quite some time in the tool as well, probably the last 4 or 5 years. And so that's another thing, again, it's here, people are using it. I just saw a great presentation by Amazon, how they're doing their Lex work, and there's sort of plugins to get these things. There's a lot of AI stuff already kind of right there and ripe for the picking. Graph databases, that's a key one. Having the ability to really scale to very, very large things. Well, we started actually on Google App Engine. Google App Engine used Google Bigtable as their graph database underlying it. So we were using that for quite some time. We recently migrated Innoslate primarily to just SQL Server, but we're looking at Neptune, Neo4j, lots of these other graph databases that are out there. And of course, we all can't wait for optical computing. And guess what? When that happens, we're going to have to re-engineer our tool again, and we're going to have to do all the things to go with that, but we need to take advantage of that because it has huge benefits. What it does is cloud computing gives us the ability to collaborate worldwide. So systems engineering tools need to take advantage of that capability, as we do. Highly recommend that, and more developers and products are starting to use that capability within our space. Also, that to me is the real instantiation of a concept we had back in the 90s called net centricity. This gives us that ability to let the fabric of computing information be able to deliver services across to you anywhere, anytime. Artificial intelligence, again, we talked about that a little bit already. It can help us find design problems, potential problems early. One of the things we've used it for also is the ability to check the quality of requirements. We check heuristics. There's 68 heuristics we check for to see how good is your model. We also use it for requirements traceability. So again, these things are here. We can do this, and they help us make decisions and find problems very quickly. Graph databases, of course, again, give us that greater storage capacity, and optical computing enables the speed of computations that we're all dying for to give us much higher fidelity modeling simulation. I still remember first doing modeling simulation back in the 70s and 80s on the Cray computer. And that Cray computer isn't close to what we have on our phones now in terms of computational power. Optical computing is going to do the same kind of orders of magnitude improvement, and that's what we're looking forward to. So what's the approach is best to handle the technological advancements and the complexity of the future? So one of the things that we're actually very excited about is this whole digital engineering strategy. Mike Griffin recently signed this out as a policy. It's a great idea. The idea is to see if they can't start moving data between all these different applications and things through the life cycle and have it then influence the next cycle and have that all linked together in a tight way. Integration is something that it's not clear where you want it fully integrated or you want it interoperable. And I distinguish between the two because you want touch points in between. Because there's a famous saying by George Box, and you all know it and you probably can all recite it with me. All models are wrong, some models are useful. That's not the exact quote, but it's close. and the reason we say that is that these models are all abstractions. And unless we have a tremendous amount of data about each object as we mentioned, zettabytes, and whatever orders of magnitude past that, you actually need to do this, then you're liable to have the difficulty of having that not really completely accurately represent the system. And so I know the digital twins, the goal but that's a hard goal to get to. And maybe it's not even achievable, but it's a nice goal. So it's a nice thing to go after, and we'll keep working towards that. Maybe optical computing can help us there. So again, why do we have to wait years? We really don't. I mean, as I said, the technologies are here. A lifecycle modeling language gives you a start, at least at a decent language for systems engineering. It's an open standard, it's free. It's designed to be the 80% solution. Nobody's claiming that's the be all and end all. You can extend it. In fact, extensions are suggested and offered in it. And so again, we've already extended it once for the SysML. We're looking at other languages that we probably ought to make sure we can cover and take care of with it as well. And it's a simple language. So again, something you can start with, it's simple, and then add it to it as you need it. Innoslate already uses cloud computing and AI technologies, and of course was designed to scale. And that's very critical. There's a lot you have to do on your user interface to deal with the scalability and responsiveness you need, particularly with a cloud-based tool. If you don't understand the latencies involved in cloud computing, you'll find out real quick when you try to do it. And of course, so we work really hard on that. So we've got a fairly lightning fast speed. I mean, I will say it feels like you're on a desktop tool, and it is scalable. We've tested it to very high levels of scalability, not zettabytes yet. And of course, other tools are beginning to realize the capabilities of migrating to the cloud. And welcome to the future. So the future of systems engineering is here. We can do it. Innoslate is that future in our minds. It's at least a starting point at that future, and we think we can keep evolving it and making it better and better with your input and your ideas. One of the things that's on our dashboard that I do want to always emphasize is there's a feedback form. That feedback form is there for you to tell us what you need, what you want, what you think's not in the tool. If we think it's in the tool, we'll email you back and tell you, hey, we think you can go this and that and that, and we'll show you where it is and the different things. And of course, you can always call support for help. But those ideas really help us a lot, and we've actually created whole new diagrams from them. We actually created Test Center, was originally started in that box. So these are the things that are actually really useful to us, and we really want to have that. So we want to continue to have that high unlimited data availability. We want to give you the ability to store and share the knowledge and research with all your collaborators, reviewers, model-based reviews, doing those kinds of things. Again, we can do all those kinds of things and help you really interact and work together. Highly secure, I mentioned that earlier. And then, of course, the AI involvement with Innoslate. I mentioned the quality checker, the traceability system, and intelligence view. Again, extremely fast and scalable. So we've got about 15 minutes for questions, and I think we have a bunch. So let's see if I can read them. Oh, so there was a question for reference shown about the book, I believe, the Integrated Program Management Systems Engineering book. That's by Wiley. It's Incosi PMI. The editor, I'm just looking at it, is Eric S. Okay, Rubinski. I'm not going to get this right. It's R-E-B-E-N-T-I-S-C-H, editor-in-chief. Should be able to find it pretty easily with that. Let's see what else we have here. So as a system engineer, graduate student, and a senior engineer at work, how can we get more exposed to new opportunities out of our current work environment? So I think that's attending the webinars, being a member of Incosi, I highly recommend, and other organizations help you do that a lot. And I think you'll find that there's a lot of thought out there and a lot of people working hard to, come up with, the future and help develop the future. So you be part of it. Let's see. Any other questions? Yeah, so let's see, we had, does LML even do everything we need? It's an interesting question. And, you know, the answer is no, probably not. But it's a starting point. It's another step along the way to where we really want to be and where we need to be. So again, that is something that's going to evolve over time. And the steering committee has refreshed itself a little bit. We've added some new people. And so we're really trying to move that forward. Another question is, I prefer using SysML. Why can't I use it? Well, of course you can. And as I said, the LML subsumed SysML provides it a taxonomy which it desperately needs. And that's important to have that ability. What would you say is one skill that a junior level systems engineer needs to have under their belt to provide the base for their future? You know, I would say one of the things that's the hardest part about systems engineering for us engineers is the softer skills. It's being able to communicate well, to write. I make the joke about when I go talk to classes at George Mason that my English 101 professor would be shocked to find out that I spend most of my time writing and that I've written several books. I think they would be totally stunned by that. But I had to learn that, and it was hard. And I learned a lot of that on my own because I didn't do as well in school with it as I should have because I didn't think it was important. It's very important. Let's see, how systems engineering, Innoslate, and IP-enabled processes are to be tested and compete to stop hacking. So, you know, that's always a tough one. Stopping hacking is probably not possible exactly, totally. Probably the best thing to do is try to discover the hacking when it's occurred, and having that built-in defense in depth capability that we're providing through Innoslate and systems engineering and internet protocols. You can go and start exploring those things and making sure that there are those points in between that catch people doing things that they really shouldn't do. Yeah, and he followed up with, is it possible at all? Probably not. So LML versus OPM, and I'm not familiar, object process methodology, and I'm not as familiar with object process methodology. What little I have seen of it, though, it has, to me, the same fundamental problem that the other languages have, where they're using constructs for the logic. And I make the joke about you need a 3D decoder ring to understand and read most of these diagrams, whereas you don't need to do that with the action diagram. It's easy to see, it's easy to understand, it's easy to explain to people, and that I think is the primary difference I see between the two. Do you hold Innoslate hands-on workshops? Yes, we do. Not only hands-on, we'll come in and work with you on your problem. That's our favorite workshop. We've done now, oh, I don't know, dozens and dozens of these workshops where we come in and start with the problem you're trying to solve. And we use the training to actually not just teach you the tool and the methodologies and stuff, we actually help you through the process and get you really rolling. A lot of people have really told us that's really helped them get out of the gate fast. Is there something called the meta model in LML? Yes, in fact, the meta model is MD relationship attribute, and of course attributes on relationships. That's the higher level, and the meta model then is basically the ontology, the language, and the relationships. Okay. You see, we've got some more here. Where or how does someone start with LML? What's the first step? So the first step, if you're interested, is go download the specification. It's at lifecyclemodeling.org. That's a good place to start. You can read that. There's a new book coming out very soon. It's called Essential LML. That'll be available on Amazon, hopefully in the next few months, if not sooner. And then I would say you can go and play with it on using Innoslate. And of course, there you go just get a demo version, and you can go and play with that to your heart's content. So that's a great way to get started. And of course, we have a lot of materials online in our help center for Innoslate.com as well. So yeah, I think you can find it lots of different places now. Let's see. Let's see, it looks like a two-part comment. System engineering must address uncertainties and come up with ways to expect, mitigate, and solve it. I think systems engineering is the owner of the system, its current use and emerging uses. Yes, absolutely correct. And I believe that the uncertainties is one of the difficult things. And we did put in the language the specific ability to put in distributions for those uncertainties, and particularly as you're early in the development phase. I do a lot of architecture level work, and at that point in time, you don't know a lot, but you can think about the kinds of things you want to know, and then sit down and think through. Well, here's the best case, here's the worst case, and here's what I more or less think it's going to be. That's a triangular distribution. That's very easy to then use as a basis for your initial distribution set for doing your analysis. And if you use that, that'll help you get started with it. And then, of course, over time, as you get better and better at it, you can use it more effectively. And you make those different distributions and refine the distributions. How can we facilitate the development of standard components, taxonomies, modules for reuse in the tool, such as joint common functions list, joint capabilities areas, things like that. Likewise with components and circuit design. So one of the things that we're working on is to be able to do more of that. We actually do have a number of these standards parsed, and we're going to try to make them more available. Our goal is to try to, we started something when we really began called Share Space. And this was, it is still on our website, and you could go down at the bottom of our website, at the Innoslate website, and find Share Space. But in there, the stuff that's there is pretty old. What we want to do is update all that, add other things, and make that a sharing space for everybody, so other people can provide inputs to that and work with it. Let's see. How does LML handle systems engineering specialties like reliability, availability, and resilience? Absolutely. Those are critical items. I've done failure modes, effects analysis, reliability kinds of analyses, things like that. Particularly what helps a lot is the logic side of it, the action diagrams let us do that, but also the ability to simulate those and then see what the random probabilities are between things. So you can look at failure modes. You can then come up with statistics between those, and again use some other analyses and bring those together in one place. And so that's what we're trying to do with this. So yes, it's absolutely helped for all what people call the ILDs. The ILDs are critical, and another thing that we try to emphasize is that the system engineer doesn't know all this, so that they have to go to the specialists and talk to them. So safety, security, your maintenance folks, everybody in the process needs to be addressed and worked with in this. OPM and LML have more similarities than differences. The biggest similarity is in their simplicity and natural approach to decomposing systems. So that was a great thing. Again, I'm just not that familiar with it. And let's see. Oh, somebody's asking about, are we going to make this available, the webinar available? Yes, we will. We'll have it uploaded and we'll be sending you links for it. Can Innoslate auto generate representation model? So I think that means both the physical and requirements can be generated automatically. Right now we haven't done the functional model from requirements. That's something we are looking at as well. So yes, the answer is we can get there. Are we there yet? Not quite yet, but we're close. So again, those are great ideas, and if you'd like to see that kind of thing, go into our dashboard on Innoslate. When you get it up in Innoslate, there's a dashboard widget, and it's called the feedback form. That's a great place to bring in the new ideas like that and things you're looking for specifically. So I think I got through all the, well, one more popped in here. What other solutions can be integrated with Innoslate for other areas like systems engineering, like enterprise architecture, tools like ArcMate and Eclipse? So we have APIs to help you with the tool integration. There's a REST API and Java APIs to help you do that kind of integration. That's how we recommend particularly tying it to other tools. Other frameworks like TOGAF and things like that, again, it's not one I'm super familiar with. We do have a DODAF dashboard that we've already created and provided for that kind of viewpoints with it. We also mapped UAF. We have not implemented that dashboard yet because we're kind of looking for a demand signal from the customer community that that's something they really want, a broad enough group that's worth actually putting the effort into building that. But it actually isn't very hard. And I believe it probably the same way with TOGAF or Zachman or any of the other frameworks. So if there's something specific somebody needs or wants there, we could certainly discuss it. It's a matter of resources and time to do almost anything with it. Let's see, and I think I got everything. So if there are any other questions, again, please feel free to email us. We're going to do another webinar coming up. So, yep. Joanna?
Yeah, so thanks again, everyone. So please join us for our next webinar. We are going to do how to perform model-based reviews next month on Tuesday, April 16th at 11 a.m. We'll do that right here at the same place. Again, as we just mentioned, we will be uploading this to our YouTube channel and make it available for everybody, and we'll send out the link to everyone as soon as that does become available. We do encourage you to visit our website and our blog, as well as connect with us on social media. So that does include today's presentation. Thanks again, everyone, for attending, and we do hope to see you again at our next webinar in April. Enjoy the rest of your day.